Pronobesh, can you hear me now?
Yeah. Could you hear me?
Yeah.
Okay.
Okay, so welcome back to the second talk of the day. Pronobesh, maybe you can start screen sharing your slides.
Yeah, I shared my screen. Could you see it?
Okay. So our next speaker is Pronobesh Maity from ICTS India, and he's going to talk about from fields to strings. Since this is a Zoom talk, it's very important that if you want to ask a question, please raise your hand so the microphone can be passed to you, because otherwise Pronobesh won't be able to hear you. And Pronobesh, also, if you find a question, so just pause and entertain the questions. So you have total of 90 minutes, but the target is that you try to finish the talk between 60 minutes. So there are plenty of time for discussions afterwards. Is that
Yeah,
okay?
sure. Yeah.
Okay, so over to you.
Yeah. So first of all, thanks the organizer for giving me the opportunity to speak here. Unfortunately, I couldn't attend the meeting in person for visa issues, but yeah, anyway, I'm going to talk about from fields to strings. This is based on two works with Matthias Gabatil, Rajesh Gopakumar, Bob Knighton, and another one is with Faizan Bhatt, Rajesh, and Bharat Kumar Radhakrishnan. Okay, so one dominant perspective before advent of ADS safety is that strings are ultimate building blocks of nature. For example, galaxies are made of matter, matter is made of molecule, and if we follow this thread, we ultimately find strings. But a different viewpoint emerged after ADS safety, which says that strings could be seen as emergent natural geometry from large N gauge theory. So rather than reductionism, this is an approach of emergence. So in this talk, we will try to argue this emergence of strings out of field theories. By the way, it's quite mysterious that a theory of fields, a theory of particles, a theory of trajectories could reorganize itself into a theory of surfaces, a theory of strings in ADS. Maldacina's ADS safety concretizes such dualities, but both sides are not simultaneously decipherable because of the strong, weak nature of the duality. So it's very difficult to portray the mechanism behind it. But there has been recent impressive progress on ADS3 safety 2 and to some extent for ADS5 safety 4 in the tensionless limit, where both sides are under control, and therefore you could ask what's the mechanism behind it. And in a different line of thought, a few years back, 15 or 20 years back, Gopakumar gave a prescription for gluing walt line into wall sheet. And he proposed that this is the mechanism for gauge string duality in the free limit, in the free field theory limit. So a natural question is that can we revisit this Gopakumar's construction in the context of this exact tensionless dualities? So in this talk, we will show that this prescription works explicitly for ADS3 safety 2 and to some extent also for ADS5 safety 4, in the sense that we'll see the Feynman graph will define something called stable graph, and that will correspond to a point in the string moduli space. That's how, starting from a field theory contribution of a correlator, we will arrive at a contribution from a string scattering amplitude. I want to stress that rather than being a proposal, this is now an explicit construction in the sense that this treble story comes out of the construction. Anyway, this will be clear in the talk. So this is the outline of my talk. I will first introduce symmetric product safety and what are covering surfaces and matrix model. Then I will show that the Feynman graph is related to this matrix model solution, and that would define the stable graph, and that would define the point in moduli space, string moduli space. And then I'll talk about some twister covering in ADS3. After that, I'll talk twister covering in ADS5. And finally, I will give an explicit covering map for ADS5, whose area will give you the familiar Feynman propagator of a free field theory. Okay, so let's start with symmetric product orbifold safety. As you all know, this is basically correspond to taking k copies of sigma model and identifying them, quotienting them by some permutation group. So naturally, there are two kind of operators states in this orbifold safety. One is the untwisted sector. These correspond to the states which are invariant under this permutation operation. And there are also twisted sector that correspond to some fields, some special fields which have some defect monodromy, in the sense that if we take any chiral operator from any of these copies and drag it around the twist field, we will arrive at a different seat, at a different copy of the original sigma model. So therefore, the twist operator induces a W-fold cyclic permutation amongst the copies of the seed theory. So you're interested in computing correlator of such twist field, but not arbitrary twist field, single cycle twist field. By ADS-SFT dictionary, that this would correspond to the single string states in the ADS3 bulk. And as I said that they have a monodromy feature. So locally, a W cycle twist field basically induces a W fold covering given by this relation. So, so near each insertion point of the twist operator, we could consider a W1 seated cover where there is a W fold covering as we move around the twist operator. And we can combine all these local coverings near all these insertion points into a global covering surface, and that is prescribed by this covering map. So this is the original space-time coordinatized by X, where the original CFT lives. And this is the auxiliary covering surface we are constructing just to simplify the calculation. So the trick of Lulinen method to compute the correlator was to uplift the calculation on this covering surface. Because, yeah, so before that, let me mention that the number of seats, the number of seated covers is given by this formula, which comes from a result from Riemann surface theory called Riemann-Harwich formula. So this basically defines the degree of the covering map. Anyway, so why it is interesting? Because on the covering surface, the twist field becomes identity because their monodromy feature is captured by the surface itself. So the computation of correlator basically becomes the computation of partition function, and it gets contribution only from the conformal map because we mapped the original S2 surface to a different covering surface. So there will be associated conformal factor given by exponential of Liouville action. The Liouville field phi is related to the covering map with this by this relation. That Liouville field is log of del of covering map. Okay. Now the covering map for a genus from a genus 0 surface to a genus 0 boundary has this rational form. This is a mathematical fact, and computing it requires to know this lambda is these poles of the covering map, and there are a set of equations to determine it called scattering equations. So to determine the covering map, which is essential to compute the correlator, we need to solve these coupled equations. Now this is a very difficult problem, but the main observation of our paper was that in the large n limit, when the twist of the fields are large, this basically becomes the saddle point equation of a matrix model. It's a matrix model where the potential is logarithmic. So as you know, in the matrix model, there are two kind. So by the way, I should say that the poles of the covering map are eigenvalues of this matrix model. So as you know, in the matrix model, there are two kind of forces. There is an attractive logarithmic potential, which is just given by this external potential. In our case, it's logarithmic. And there is, of course, this natural van der Monde determinant part, which gives the Coulomb repulsion. So under the effect of these two forces, the eigenvalues will try to localize on a set of curves, on a set of cuts on the Riemann surface. And this eigenvalue distribution is precisely captured by something called spectral curve. Yeah. Now, as you can see, the spectral curve is basically like a hyperelliptic function. It has n-3 A cycle, n-3 B cycle. So if we specify this A cycle period and B cycle period, we will specify the spectral curve that will specify the eigenvalue distribution. That means that will give you the covering map. So each spectral curve specified by A and B cycle period will give you a particular covering map. So in passing, I should mention, or I want to mention that it's interesting that we find that the square of the spectral curve is actually the Schwarzian of the covering map. And this is true in the strict large n limit. In the limit where capital N is infinity, we find that the square of the spectral curve is the Schwarzian of the covering map. We don't know at finite n how does the okay, we'll later see that this spectral curve square will define a metric on the covering surface. So it's an interesting open question. How does the stable metric will differ from this Schwarzian? Anyway, this will be clear again. I will tell it in detail.
But the curves you are considering are hyperelliptic, are not the generic one. are hyperelliptic or not?
Yeah, could you hear me? Yeah, right. Okay. So it's the solution of this logarithmic planar potential matrix model. If you compute the spectral curve, you will get this form. I'm not assuming it, but it's coming out of the calculation. Yeah.
It is not, it is this way. It is not the most generic G loop Riemann surface.
It's sorry, I couldn't understand the question, but
I mean, how many parameters this curve? Which is the dimension of the modular space of this?
I understand. Yeah. The dimension is 2 times n-3. So this n-3 cycle period and b cycle period specify your eigenvalue distribution, specify your spectral curve. So
this Riemann surface is a special Riemann surface that is not like the string theory is not living on this. This is the spectral curve of the matrix model, and they're always hyperelliptic.
yeah,
It is
this is,
hyperelliptic because it comes out of a computation on the matrix side.
yeah, I still haven't come to the string side yet. Yeah, we are talking about the field theory computation of the correlator, and yeah, the matrix model is coming out, and this is a branching surface. It's nothing to do with the string theory. So yeah, is it clear or? Okay. So yeah, so let me talk about some diagrammatic of this orbifold safety. This was put forward by this company, Pacman, Rastil, and Rajanath. So the trick is like first to consider a Jordan curve. That means a curve passing through the insertion points of the CFT correlator, enclosing the infinity. So this is x equals to infinity, and this is the original space-time where the CFT lives. Now the trick to the prescription to find the Feynman diagram is to consider the pre-image of this closed curve under the covering map. So for each covering map, you will get a different Feynman diagram. Now, as you can see, this colored loop was enclosing the point infinity, and therefore in the pre-image, these blue dots are nothing but the poles of the covering map. So I want to stress that the poles of the covering map lie on the center of the colored faces in the Feynman graph. For example, this is a Feynman graph for computing this twist correlator 555. Everyone has the twist 5. And therefore, what happens in the large n limit, in the large twist limit, is that this near the weak contraction between two vertices, all the poles of the covering map, which lie on the center of the colored faces, come closer, and they form a dual Feynman edge. So this is the original Feynman weak contraction, and these poles of the covering map are forming a dual Feynman edge. Now recall that in the last few slides, I told you that these poles of the covering map are nothing but the eigenvalue of the matrix model, and in the large n limit, they are coalescing to form a cuts of the spectral curve. So manifestly, we can see that the spectral curve is defining a cut, which is forming a dual Feynman graph. So this will be clear here. So for each spectral curve, we will get a Feynman graph, and the spectral curve defines a cut structure, which defines the dual Feynman graph. So the original Feynman graph is given by this colored thing, and the dual Feynman graph is this skeleton figure. Okay. And what are the periods of A and B cycle period, A and B cycle period of the spectral curve? They're nothing but this, this number of eigenvalues localized here, which is basically the number of weak contractions. So this A and B cycle periods basically becomes the fraction of eigenvalues localizing in between two vertices. So this is fine. So we have found the covering map by solving the matrix model. Now the remarkable thing is that the spectral curve is not an arbitrary quadratic differential, but it's a very special kind of differential called stable differential. Now what is a stable differential? It's a quadratic differential which is holomorphic except with a set of double poles. So if you square it, you can see there will be set of double poles and there will be set of zeros. So stable differential is such a differential which has double pole and zeros, but a defining property of stable differential is that the length between two zeros would always be a real number. And this is precisely satisfied by this spectral curve, because we have seen the length is nothing but the fraction of eigenvalues, the number of weak contraction, which is rather a rational number. So it's always real manifestly. So the conclusion is that the spectral curve actually defines a stable differential. And for each stable differential, we can actually define something called stable graph, whose vertices are the zeros of the stable differential, and whose edges are something called horizontal trajectory, which means some trajectory along which the length will be real. Anyway, this is not important. So why this connection is important? This is because of a famous theorem of stable, which says that a unique stable differential parameterized by his stable length correspond to a point on the punctured Riemann sphere with specified real numbers. So at each puncture, we specify a real number. Now we have seen that for computing the twist correlator, we have to sum over all possible covering maps, and each covering map corresponds to a spectral curve parameterized by A and B cycle period. And in the last slide, we saw that A and B cycle period are basically the stable lengths. So if you follow this thread to compute a field theory correlator, each covering map basically corresponds to a point in the string moduli space, because this is the string moduli space, right? This is the space moduli space of punctured Riemann sphere with n specified points. These are like the, if you consider a tachyon scattering amplitude, these are like the moment of the tachyons. So by this way, following this thread, we find that there is a connection between a Feynman graph contribution or a covering map contribution to a point in string moduli space. Okay, this was satisfying that we could reorganize the Feynman graphs in terms of some covering the moduli space of the string. But what about the summand? What about the integrand? So I told you earlier that the summand is nothing but exponential of a Liouville action. Now, if we use our dictionary of matrix model, spectral curve, and stable differential, this triality, then this Liouville action is nothing but Nambu-Goto area under this treble gauge. By stable gauge, I means if we consider the matrix set by the stable differential, for example, this matrix D2Z, phi SZ.
Hello, can you
Yeah.
hear me? I have a question
yeah.
about the area here. So in the punctured case, is it the reduced area of the Strebel differential? Like, because in that case, like if you just take the genus zero and punctures, how do you define area?
We have a metric on the covering surface, right? Set by the stable differential.
Yeah,
And
but that area is divergent, right?
Correct. That area is divergent, so you need to regularize it. In fact, in an explicit construction, I will compute this area at the end of my talk, and there will be a cut of length scale, and that will appear in computation of the correlator. So what happens is that there will be a cut of, there will be a UV divergence, but that basically means you have to, do some wave function renormalization kind of stuff. But I'll come to it.
Yeah. Another question. So are you going to have a formula for this area over the moduli space? How it depends on the moduli?
How it depends on the module.
Do you like say that the Strebel differential defines this area, right?
Yeah.
So do you know how this area changes over the moduli space as a function of the position of punctures, say?
Yeah, I understand your question. Yeah, for that you need to solve a setup. So I told you this equation, right? So what you're asking that how does the area depends on this length, stable lengths?
No. What I'm asking is that how the area area depends on the position of the double poles of the Strebel differential. Do you know, or like this you don't know that?
Yeah, I don't know that, but yeah, for the case of symmetric for orbifold safety, we have explicitly computed this area and we reproduce the familiar expression of symmetric orbifold correlator in terms of, so okay. To summarize, I have to say that this is a tricky business, but you need to take a set of cards around each double pole, and then you should be able to compute the area, right?
Yeah, that's correct. But the problem is that you don't know the Strebel. Like, say that I given the position of the punctures, double
Yeah.
pole,
Mhm.
and then the question is that what is the Strebel? How you define your Strebel? What is the position of the zeros, so that the quadratic differential forms a Strebel differential,
I see. Yeah,
right?
that I
Yeah.
agree.
Yeah.
Mhm.
My
So
question is that the how is it do you have any methods to like see the area changes as a function of the double poles without finding the quadratic the Strebel differential itself?
yeah,
Like
that I
like
agree. That we don't know because we don't know any explicit example of stable differential for a 4-point function. Yeah.
I see. Okay, we can talk about this more. I'm interested in that content.
Yeah.
Thank you.
So this is basically the flowchart, whatever I told so far. This middle side is field theory, this side is string theory, and this left side is matrix model. To show the connection between field and string, we took help of this matrix model. And this looks like some triality, but yeah, maybe this doesn't make sense. So this is what is happening pictorially. What is happening is that we're considering twist fields of large twist, means large number of weak contractions, and basically all these different propagators are gluing together to form a wall sheet. And this is the Strebel graph, which is basically going through the weak contraction, and the Strebel lengths are measuring the number of weak contractions, which are integer in this case. Yeah, so that's the first part of my talk. Now, in the next part, I want to go in a bit detail into the wall sheet theory. So the wall sheet theory of ADS on ADS 3 times S3 times D4 with K equals to 1 unit of NSNS flux is based on a WGW model based on this supergroup. And of course, there is a T4 sector. Now, because it's at level 1, as is familiar in 2D safety community, we can represent it in terms of a free fields. So it can be represented in terms of 4 symplectic bosons and 4 spin-up fermions. And in this paper, this company have shown that from a word identity structure, basically considering OP of these symplectic bosons with the spectrally, okay, I didn't explain what are spectrally flows, but from Maldacena-Oguri paper, we know that in ADS3, there is a spectral flow automorphism of the current algebra. So along with the standard highest rate representation, we also have a spectrally flowed representation and corresponding vertex operators. So anyway, these details are not important, but what I want to say that this free fields like variable obey some incidence relation like the twisters. So by twister, I means for every spacetime point x, we can define projective coordinates mu and lambda, which obey an incidence relation like this. And this same kind of relation comes out of the calculation from the wall sheet fields. So from here, in fact, we can define ambitwisters this out of these free fields. So these are the bosonic free fields. We are defining these 2 kind of twisters, and they obey this ambitwister constant. Ambitwister constant basically means this that y times z inner product should be 0. And this relation is basically needed for a gauge symmetry to quotient out the, so we have this group PSU11/2. So to quotient out this S2E1 subgroups, we need this relation. And that's different.
Sorry.
Yeah.
Quick question. I'm not super familiar with these mu and lambda. One should think of this as a function of x, or what is the meaning of that equation? Mu
Yeah.
plus x lambda equal to 0.
So this basically tells that for each x, you have a set of mu and lambda. So this is the twister correspondence that for every point in the space-time, you have a line on the twister space.
Sorry, and a dot are what are these indices on?
This a and a dot are this, this spin or helicity like variable. And but yeah, I'll give an introduction to twister theory in after few slides, and maybe you can get
Okay.
yeah.
Okay.
Yeah. So this SL2 or currents have this familiar Wakemuth representation in terms of the fields in ADS3, where phi is the radial direction and gamma bar parameterize the boundary sphere. And they have also this standard, representation in terms of fields, which we saw twister fields. So comparing these 2 kind of expression, we can actually find the twister like bosonic variable, these twistor variables prefills in terms of ADS3 coordinates. And after finding this, we found that they do not obey the twistor incidence relation precisely, but they obey a stringy version of it. In the sense, the incidence relation is the right-hand side is not 0, but the right-hand side depends on the radial profile of the string. So this basically says that the dual of free symmetric orbifold CFT is ADS3 string theory, which is pinned at the boundary, but they still have a radial profile, and that is manifest from these relations. And we also computed the stress tensor out of these free fields, and rather surprisingly, we found it to be the Schwarzian. So we have shown before that the Schwarzian is your stable differential. So in some sense, the stable differential is coming out of, it looks like this stress tensor of the wall sheet. We do not know any precise reason why this is happening, but yeah, something this is coming out of it.
I think there is a precise reason why this happening.
Yeah.
You just start with the hyperbolic Riemann surface,
Mm-hmm.
and there is you can write some differential equations on that,
Mm-hmm.
and then the hyperbolic matrix is basically related to the real monodromy of that, having a real monodromy for the solution of that equation. And if you take the certain limit of that differential, it basically
Mhm.
reduces to the Strebel differential. So that relation reminds me what's happening there. Basically, you write some Fuchsian equation, all right, like some del square psi plus 1/2 t psi, where t has like double poles,
Mm-hmm.
almost. And then this t becomes a Strebel differential when you basically scale, like, then okay, this differential equation defines a metric on some bordered Riemann surface which borders of length L, and if you take
Mhm.
to this length L to infinity,
Mhm.
that t becomes a Strebel differential. And in that equation, actually the Schwarzian derivative of the ratio of the solution is equal to the Strebel differential itself. So there's a way to go around this. So it reminds me what happening there. I don't know if you have any knowledge of
I
it.
see. Yeah, I did know it better, but yeah, thanks. So we have to consider hyperbolic metric on the space. Right?
Yeah.
Sure thing.
Sorry, am I audible? Yeah.
Okay. Yeah. Anyway, thank you. Just
So-
wanted to point it out.
So you have to consider a hyperbolic metric on the world sheet, is it?
Yeah, like you take some hyperbolic metric, say that, I mean, it's not entirely hyperbolic. You just take the hyperbolic metric with it on the Riemann surface of borders of length L,
Mm-hmm.
and you graph cylinders onto those borders. So it's
Mm-hmm.
partially hyperbolic, partially flat. And
I
then you take the L goes to infinity limit, and then what appears in the surface, there is a Strebel differential forming.
I see. Okay. Okay,
So,
thank you.
okay, that's just
Mhm.
I haven't like gone through all details, but that's what should be happening. And in that case, there's a natural relation between solutions that you wrote in that particular the ODE and
Mhm.
it's Schwarzian and the Strebel differential in that limit. So there, yeah, the covering map that what you call covering map is maybe it's like a related to ratio of those solutions.
I see.
Anyway,
Mhm.
thank you.
Okay, thank you. Mhm. So given a covering map, which is basically a rational polynomial, because it's a covering map from genus 0 to genus 0, we can actually compute the twistor-like variables, and these are also rational polynomials. Anyway, these are not important. The only message from here is that the twistor variables are rational polynomials of the holomorphic fields. Now coming to the story of ADS5 times S5, there have been also a proposal by Gabriel and Gopakumar of the dual of free n equals to 4 super-Young mills based on this field content. So this Gi and this Yj. So there are 8 bosonic variables now and 8 fermionic variables now. This alpha is 1, alpha goes 1, 2, and alpha dot goes to 1, 2. A goes from 1 to 4. And there is also a ambitwistor-like constraint, and that appears for similar reason to quotienting out the PSU part. So this is based on PSU 2/4 at level 1. The new perspective here is that the sigma model is based on the twistorial target space, not on the ordinary ADS5 times S5 target space, but the twistorial version of it. Yeah, this will be clear in my next slides. So they imposed a physical gauge constraint on these variables. The gauge constraint says that all the modes which lie between these OH defined by the spectral flow amount, and this R is the mode number. So all the modes that lie in between these OH are active, and all the modes lie outside this OH are inactive. So these are here lies all the creation and annihilation operators. So we can view this finite number of OH modes as exciting a discrete set of string bits along the wall sheet. Now we want to discuss a classical analysis of these ADS5 twisted fields and see how the notion of covering maps that was there in for ADS3 could generalize for this case as well. So yeah, so before that, let me talk about the twistor space. So if we consider a complexified Minkowski space in 4 dimensions, then the twistor space basically means a subset of CP3, which is coordinatized by these homogeneous coordinates, these 4 coordinates, and there is a scaling symmetry. So it basically coordinatized CP3. So for each space-time point, we have a complex line in twistor space, and the line is given by this linear relation. So this twistor incidence relation basically gives you a correspondence between these two spaces, ordinary spacetime and twistor space. Anyway, so this incidence relation can be also written in this matrix form, where you are acting a matrix defined by this not 2 cross 2. This is like 4 cross 4, and acting on this twistor is 0. Now for ADS5 also we can define a twistors. This is in the following way. First, we'll try to coordinatize CP5. That we can do.
A question. Previous slide was in how many dimensions of Minkowski space? This is how many?
This was for 4D Minkowski spacetime. Yeah.
4D. So you have 4 complex dimensions in the complex Minkowski space.
Yeah.
So how is it a subset of CP3? Isn't that just 3 complex dimensions and you need 4? I'm just missing some basic, something very basic here.
Okay, let me keep me 1 minute here. So yeah, so I'm not telling that each point in X correspond to a point in lambda and mu. So a point X correspond to a line in twistor space. So you need 2 points to define a space-time point. So is it clear? I mean, the correspondence is not between X and mu and lambda, rather X and this equation.
I'm just sorry, just to dwell on this for 1 more minute. In the first line, you say complexified Minkowski space. So that's C4, right?
That's C4, yeah.
So how can it be an open subset of CP3, which is lower?
No, I'm telling the
Maybe.
twistor space corresponding to a Minkowski space is an open subset of CP3, where a point which is specified by 4 complex number, as you are saying, is specified by a line in twistor space.
I see.
So this, this correspondence is non-local. So a point is specified by the line. Yeah. Yeah, even for ADS5, okay, for CP5 we can write a coordinate in CP5, a point in CP5 in terms of a matrix, Q symmetric 4 cross 4 matrix with the projective invariance, because you can see the degrees of freedom match. For CP5 you have 5 complex degrees of freedom. For 4 cross 4 antisymmetric matrix you have how many? 4 times 3, yeah, 6 degrees of freedom, but you are quotienting out this projective invariance. So basically there are matching of degrees, number of degrees of freedom. Anyway, now if we consider this metric with this parameterization, so you can directly check that this metric is becoming the ADS5 metric in the point care coordinates. where this xb basically correspond to the boundary of ADS pipe, and this r is the radial direction in the point care coordinates. Okay, now we defined two twisters like zi and yz, which obey these incidence relations on the boundary. That xb on zi, xb acting on z is 0. This gives a twister incidence relation for these variables. And the second one is similar relation. This gives another twister relation on these second variables. And they naturally obey this ambi-twister constraint. And then I'm skipping many technicalities, but basically in this paper, this Adamo, Skinner, and Williams basically put forward twister incidence relation in the ADS5 bulk, which looks like this. These two variables of ambi-twisters are related by an incidence relation where x is what coordinate, x is a matrix what coordinatize the ADS5 bulk. So because xij is antisymmetric, this naturally satisfies the ambi-twister constraint. And I am saying it multiple times that this is very necessary to quotient out the E1 subgroups of the supergroup from the wall sheet analysis. But anyway, these are all kinematical level. So to describe the string configuration which capture the dual field theory, we need to consider we need to take them depending on the holomorphic and anti-holomorphic coordinates on the wall sheet. So we uplift basically the coordinates to be the fields, the wall sheet fields like this. And then we are assuming, so this is still an assumption that this ADS5 incidence relation is obeyed. Now, for string dual to free super Yang-Mills theory, the string should be near the boundary of ADS5. So we could take them to be the original, the ordinary incidence relation like this. So there is no radial profile. So if we consider the ordinary incidence relations instead of the bulk ADS5 incidence relation, and then take derivative with respect to del bar, we see that del bar of x has a 0 eigenvector. So what does it basically mean? It means that del bar and x has one entry to be 0 in the block diagonal form. So this basically tells you that x, the string configuration in ADS5 locally can always be taken as a holomorphic embedding into the boundary of ADS3 subspace of ADS5 bulk. Okay, maybe these were too technical, but let's consider a simple setup where the 4 points on the boundary correlator are on a plane. So this is not a restriction for 2, 3, and 4 point function of the superangles. You might wonder how can the 4 points be always in a plane? This is because of the use of the conformal symmetry of these superangles. So under this setup, the string would lie on a ADS3 subspace of ADS5. And then we can always write the string configuration in the bulk in terms of a holomorphic field and anti-holomorphic field. And the twister variables will be like this. So as I did in the last, before few slides, these covering maps, this VZ and V bar Z bar are rational polynomials, and the twister fields will also be rational polynomials. And this fits very nicely with the proposal of Gabardelle and Gopakumar, who was saying that we have only wedge modes excited. So rather than being an infinite sum, this is a finite sum, and therefore we expect the twister fields to be the rational function of the holomorphic fields. So this is in some sense fitting together. Yeah. So now, after all this general treatment, let me concretize a special explicit construction of the covering map. Let's consider an n-gauge invariant scalar operator in n equals to superangles, which is given by sum of product of different weak contractions. Now, for a particular 2-point function joining these 2 points, consider this following covering map, which is a rational polynomial, and these 2 points can always be taken on a plane. This is a well-known fact. So corresponding wall sheet points, the vertex operators should be inserted at z. We can take them to be inserted at z equals to 0 and z equals to infinity. and this is the covering map for this two-point function. So we are considering a particular two-point function between xi and xj and writing a covering map for that. Now it is convenient to go to a different space coordinatized by u rather than z, given by this relation. So what does this map do? This map basically transforms the sphere into a strip of length w. And the points where the vertex operators are inserted, we are claiming the vertex operator are inserted, are basically becomes plus minus I infinity, two imaginary infinities. On this space coordinatized by u, the covering map becomes very simple. It becomes basically tan map. Now the surprising thing is that this tan map is the only map for which the Schwarzian is a constant. And if you compute the Schwarzian, it's just 2 pi square. But on the strip with two insertion points, the stable differential is also simple. It's just du square. So we see that at least in this strip, in this u coordinate, we see that the stable differential is manifestly the Schwarzian. Now you might wonder, okay, this is maybe coincidence, but this is a coordinate independent statement because the Schwarzian is a quadratic differential. So this is true in any coordinate. And that for this two-point function, the stable differential is basically the Schwarzian of the covering map. The covering map we considered, and which is natural from the Gabardel-Gopa-Kumar prescription, because the covering map was the rational polynomial, because only the wedge modes are excited. So the strip up with W is nothing but W double lines glued together, and we can try to compute the Nambu-Goto area and see whether it indeed reproduces the two-point function, which we all know 1 by x squared. Anyway, so to compute it, we again go to the stable gauge, this matrix set by the stable differential. Then in the u coordinate, the area is nothing but the area of the rectangle, which is width times length, but the length is infinity. So this is formally infinity. So we need to put a cutoff. So we cut off them at length scale L. And so we put a space-time cutoff epsilon, and then we put this cutoff L. So if you use the form of the covering map, the tan map here, you can explicitly get that the length is given by log of xij square by this cutoff square. So from it, the Nambu-Goto weight, which is exponential of area, which is exponential of width times length, is nothing but the two-point function. So we showed a particular covering map, which is reproducing the familiar result of the two-point function of a free field theory. Now for a multi-point correlator, we have defined weak contractions at different level. So we consider this two-point function and found the covering map. So piecewise we have the covering maps, but how they are glued together, this is something we don't know. But to compute area, we can just sum over them, and we can write the correlator, the field theory correlator, as sum of product of propagators, but the propagators are given by exponential of areas. So basically exponential of sum of areas. So this is the result, which shows that you can write a field theory correlator in a Nambu-Goto like area, in a Nambu-Goto weight, where the Nambu-Goto area is given in the stable gauge. Okay, that's it. Now it's okay. I have still 13 minutes left. I want to talk about some take-home message. So what do we learn from all this calculation, all this analysis, is that each Feynman graph of the field theory can be associated to a point in the closed string module space via the stable construction. And this is not a proposal. This is coming out of the computation for the case of symmetric product orbifold CFT. And to some extent for 4D super Yang-Mills theory, we saw that for two-point function at least, this is manifestly true. And the sum of Feynman diagrams defining the correlator goes over to an integral over the closed string module space. The second message I want to stress is that the wall-sheet fields can be seen as holomorphic covering map to the twistorial target space. So maybe we should liberate our notion of string target space from ordinary space-time to a twistor version, and then the holomorphic covering surfaces will define you the wall sheet. For outlook, I want to mention that the ADS5 twist incidence relation that I told earlier was an assumption, but it would be very nice to get it from a refined worldsheet analysis, and this is in fact in progress. At some point, I told you that the stable differential is the origin of the covering map in the large twist limit, in the infinite twist limit. But of course, it's exciting to see how does it differ if we take 1 by n correction, 1 by twist correction. Remember that capital N is not the familiar standard capital N, but it's twist here. And this is in fact in progress, and we found that in the first subleading order, the Schwarzian is still the stable differential, but at the second subleading order, there are interesting correction to the Schwarzian. But yeah, maybe this will, yeah. The thirdly, the story of covering surface as the string theory first appeared in the context of Gross and Taylor, who studied 2D Yang-Mills and said that this is basically a string theory. So it's exciting to find an explicit worldsheet dual for this 2D Yang-Mills, and this is something I'm doing with Shota Komatsu. And we found some exciting result in the sense that the string is some TT per deformed version of some other theory. Anyway, there is a familiar program of hexagonalization for n equals to 4 super Yang-Mills, where we find the correlator by gluing different hexagon patches, and maybe our story will combine with them in some when we take perturbation, when we take interaction into account. Also, it would be exciting to compute the Mellin amplitude of perturbative n equals to 4 super Yang-Mills, and to show whether it has anything to do with our covering surface. So hopefully all these different approaches to find string out of field will combine to give a coherent picture finally. And yeah, with it, I want to finish my talk. Thanks for your attention.
Okay, thanks, Pronobesh. We have plenty of time for questions and discussion. So
Yeah, sure.
Okay. Just to try to summarize what you are doing. You are not computing the correlation function or amplitude for all the possible string excitation, but only for the massless one, or what? From a string point of view, which correlators amplitudes are you computing of which fields?
I see. Oh, yeah. So there is a parallel story from computation from the worldsheet side, where they, yeah. So for the symmetric product orbifold safety, I'm computing the twist field correlator. On the string side, these correspond to the spectrally flowed vertex operators. So the W twisted sector correspond to a W spectrally flowed vertex operator in the, yeah. So is it clear, or I need to?
I have understood that the words, but physically they correspond to.
Physically, physically they correspond to winding string, right? That is what is happening. The covering surface, we are claiming that the covering surface is the worldsheet, and the covering surface wraps near the insertion points,
Okay,
W
but
times.
they are scalars.
They are
From the point of view of IDS5.
from the point of view of it. Yeah, I understand what you're saying. So far, we only talk about the bosons, right? There is no fermion.
Yes, but you have a
in
IDS5, you have a
but there should be
spectrum.
fermions. Yeah, there should be fermions. So that's why I mentioned this. I want to do some classical analysis where I'll talk about only fermions. But yeah, indeed, it will be interesting to incorporate the fermions in the story. For example, here I wrote the ADS5 spacetime, but I didn't write the S5 part, right? There will be associated S5 block diagonal part. And these twisters, there should be a fermionic counterpart here. And all the things I'm describing here should be generalized in a more complete story.
I think to answer your question, maybe there's a WZW model on the world sheet. And Pronobesh, is it right that you are computing some correlation function of of the vertex operators in the WZW model, right? For the ADS3 case, let's say.
Yeah. I'm
I see. So-
computing the correlator of vertex operator of this PSU11/2
Yeah, so
WZW model.
there is a super group and there is a sigma model with the target space being that super group. And it has some explicit free field realization. So you're just computing the correlators of these Xi, eta, and psi, and chi, some combination of these fields.
Yeah, exactly.
It's very stringy. So it's in the free, it's a free theory on the boundary. Yeah. Yeah. Well, at large K, it would become the usual. Yeah, but at this point, you know the exact dual theory. It's the symmetric product orbifold, which is just a free theory up to some.
Hey, can you comment on the connection between level action and area of the Strebel differential, and how does it come from? Where does it come from exactly?
Yeah. 1 minute. So the Louisville action came from the computation of the symmetric orbifold correlator, right? This is standard, just Lonin-Mathur type analysis. But what turns out from a semi-classical analysis of ADS3 wall sheet is that the Louisville field is actually the radial direction, the radial field. So in ADS3 you have three
yes.
fields, right? The radial fields and the two fields parameterizing the boundary of ADS3, or the S2 slices of ADS3, and also there is a radial field. And the Louisville field is actually the radial field. I have written it somewhere. 1 minute.
Yeah. Okay. I think I see what you're saying. Also, can you scroll back to the picture that you show with the Strebel differentials?
Yeah.
That one. So on the leftmost one, are they this like blue, red? Are these lines are vertical trajectories? Yeah,
These
those
lines
double
are
lines.
vertical. Yeah, exactly.
Yeah,
These are
interesting.
vertical trajectories. Yeah, exactly. Yeah.
I see. And the like last question. So you said that the metrics model giving you this whose spectral curve becomes Strebel differential, right? Can you
Yeah.
give some detail on the like how it comes to be, like, or what? Get some can you give some intuition behind why that's the case? If it is not too
I
hard.
mean, okay, you mean qualitatively? Okay, so the stable differential has this form, right? If we square it, the spectral curve square, it has the form of stable differential. The only check we need to perform is that whether the stable lengths are real.
Yes.
The length between the zeros are real or not. And that is precisely satisfied by the construction, because that was counting the stable length was counting the number of eigenvalues,
Mm.
right? Because
So I mean, what I was wondering is that, okay, you say that you want to find a metrics model whose spectral curve is Strebel differential. Of course, that means that you need to impose this reality conditions. And how does that determines this like a log? You show some logarithmic potential, right?
yeah.
How does that come from?
How? Okay. You want to go in the reverse direction from a
Yes.
stable differential, I say. So, but these are not generic stable differential. These are integer stable differential. The stable differential.
I see. So the alpha ends are here are like integers, is it? Or
Yeah, exactly.
I see.
They are integers. So these are like arithmetic. Yeah. Anyway, these are
Yeah.
called
What about the generic case? Or like when I set them to equal to some constant rather.
I mean, here we are taking large n limit, right? Large twist limit. So in principle, any real number can be approximated to be nearer to a rational number, right? In the large n limit, and in some sense, we are populating the entire moduli space. So we have this rational point.
Decorated moduli space, right? Where you also include the lengths of. I see. You're kind of going to the boundary of the decorated part of the moduli space in certain sense. Am I correct?
Yeah, in certain sense, yeah.
Okay, I see. Very interesting. Thank you.
Thank you.
Any other questions or comments?
Well, I guess if there is no more, I just have a very simple question again about just this twister geometry. Could you explain just a bit more slowly about the ADS5 twisters? What is happening exactly? What is these 8 variables and what? Yeah, just
Yeah, yeah, I have some extra slides, maybe 1 minute. Yeah. So yeah, so let's consider the boundary of ADS5. We have a 4D boundary. So in the complexified Minkowski space, I told you that given a point in the Minkowski space, we have a line in twistor space. What does it mean? It means that you have these two incidence relation or two twistors for the same space-time point. Then you can solve it and find the point in the boundary of ADS5, point in the complexified Minkowski space as written in terms of two twistors like this. Basically just by solving this two set of equations. Now for ADS5, we have similar incidence relations, right? So are you trying to understand the incidence relation for ADS5 or?
maybe this is all well known. I'm just unfamiliar with all these equations and
Oh,
this.
I see. So yeah, so then this is complexified Minkowski space. We need to take some real slice or we have to put some reality constraint. And then given a point, okay, what should I stress on? 1 minute, sorry. What I want to say that, yeah, in ADS5 we have this twistorial incidence relation, means that this xij correspond to a point in ADS5 and this zi and yj correspond to, you know, the line in the twistor space. So given two twistor, you can get a point in ADS5 in terms of them. But okay, so do you want to understand some geometrically, is it? Or
I guess the details are in the
May-
paper, so maybe I can read and ask you.
yeah,
if
maybe
that's okay. Yeah.
yeah, I'm messing around, but yeah. So basically you can write ADS5 in this way. The ADS5 metric, which is a 4x4 antisymmetric metric, is given by this some matrix which parameterize the boundary plus a radial direction. And then corresponding to this matrix, you have some twistors, which are Z and Y, and they obey incidence relation. And incidence relation is like this.
Okay. Thanks.
So yeah.
Any other questions or comments? Maybe from other participants in the Zoom? Okay, if not, let us thank Pronobesh once again. Okay, thanks Pronobesh, and
Okay. Thank you.
Okay, this is an announcement that unfortunately Manki Kim had some emergency and had to return to the United States. So he will not be giving the talk after lunch. The talk will be canceled and instead